Good afternoon, and I welcome you all to this lecture session of the course Laws of Thermodynamics. Last class we discussed few problems in relation to the application of first law, that is the conservation of energy, to an open system. So today we will discuss another problem, another interesting problem, and then after that we will start the second law of thermodynamics. So let us now concentrate on the problem which we will discuss today. This problem 4, 3 problems were solved last class. A mass loaded piston cylinder containing air is at 300 kilopascals and 17 degrees Celsius with a volume of 0.25 meter cube. While at the stops, V is equal to 1 meter cube. An airline 500 kilopascals 600 K is connected by a valve that is then opened until a final inside pressure of 400 kilopascal is reached, at which point T equals to 350 K. Find the air mass that enters, the work and the heat transfer. Now let us see this in the board. Now the problem is like this. There is a piston and air whose initial state 1, which is given by P1 equals to, in the problem which is given by P1 is equals to 300 kilopascals, and T1 is 17 degrees Celsius, that means 290 K, and the volume V1 is 0.25 meter cube. Okay, this is the state 1. Now what is the problem? Problem is this: air flows through this. When the valve is open, air in the line, this is the line, flows through this cylinder. So line pressure Pi, that is the line pressure, this is the I, state I. The line pressure Pi is 500 kilopascals. The line temperature is given by Ti 600 Kelvin. This is given. Now the problem is that as soon as the air enters, the piston, the mass loaded piston goes up and it hits the stop. Now the question tells that at state 2, that final state, let us consider the piston hits the top before the final state. This is the final state of the piston, before the final state is reached. That means here the condition, the state point is 2, this is the final state. We consider the piston reaches the stop before the final state is achieved. I will tell how do you know it. But at this final state, P2 is equal to, the P2 is given by 400 kilopascals, 400 kilopascals. T2 is given by, T2 is given as 350 K, and the volume that is at stops, it is written the volume at stops is 1 meter cube. That means when the piston reaches the stops, the volume is 1 meter cube. Now this type of problem is like this. You have to understand, when the air goes in, this mass loaded piston, it pushes the piston and piston goes up. There is a displacement of the piston, and as it goes up, the work is done by the system. Now this case, this type of problems, when mass loaded piston is there and it is pushed by air, it is always going with or expanding with constant pressure. We have to assume that this process is such that this is a constant pressure process. You have already come to know what is meant by quasi-static process. That means it is almost a very slow process, quasi-static process, which passes through number of equilibrium states, expands in such a way that the weight of the piston is always balanced by the pressure within the gas or within the air, that pressure force within the air. So pressure is balanced by the weight. So at every instant pressure is same until and unless it hits the stop. That is the pivotal concept of this problem. So piston expands under a constant pressure. then when it hits the stop, if then air still flows, then the pressure increases. So therefore, when it just reaches the stop, pressure is same as the initial pressure 300 kilopascal. When we know the final state pressure is 400 kilopascals, that means the piston has reached the stop. After that, air still flows, so that the pressure increases. In that case, the pressure is balanced by the piston weight plus the reaction at the stops. So that is the problem. So therefore, this problem is very simple now when you understand the problem this way, and we can write the mass conservation. From the mass conservation, we can write that m2 minus m1, that is final mass minus initial mass, is the mass that has entered through the line. Now m2 is found out by what? M2 is P2 V2 by R T2, and m1 is P1 V1 by R T1. So P1 P2 V2 T2 is given, P2 V2 T2. Similarly, P1 V1 T1 is given. So m2 and m1 can be found out. So therefore, we can find out the value of mi dot. Now this value, if you calculate, you use R for AR 0.287 kilojoule per kg K. So it is AR. So you get the value of mi dot, which comes out to be, if you calculate the answer I am giving, 3.082 kg. 3.082 kg. Now I write the energy equation for this finite process. Energy equation is also very simple, that change in the internal energy of the control volume. We have considered this as the control volume. We have considered this as the control volume, and here the control volume does work. So control volume does work, W, and also heat transfer is there, because in the problem it is told the mass of air that enters, work and heat transfer, and you consider first the heat added to the control volume Q, and this is the positive. If the result comes negative, then heat will come out. Let us see how we will do. Now the change of energy, E2 is the specific energy, M2 E2, the change of energy in this, the control volume, equals to what? M2 E2 minus M1 E1, or rather you can do this way. Okay, this is the change in energy in the control volume equals to the inflow of energy, that means Mi into the energy which is coming through this with the flow, which is the flow energy, which is nothing but the H, enthalpy. This we have told that U plus PV. So this is enthalpy is there, flow work is added. So in that case, we can from the beginning write this since the within this cylinder air is at rest. So therefore, this is only the intermolecular energy, so that you can understand. So this is the energy which has come in, and at the same time it has received heat and it has delivered work. So this is simply the conservation of energy, which we can get by integrating the, as I told earlier, the general energy equation in the rate form, integrating with respect to time. But it is not required all the time to remember that equation. You can state right from the concept of conservation of energy. This is the rise in the internal energy of the control volume, that means the internal energy of the tank. Then this equals to the mass which has entered, Mi associated with its energy, which is enthalpy, because internal energy plus the flow work, and we neglect the kinetic energy and potential energy, plus the heat required, heat received and the work done. Now here you see we know M2. Now U2 is CV, we have told CVT2, and U1 is CVT1. So therefore, if you substitute this, we know U2 and U1. With value of CV for air is equal to 0.717 kilojoule per kg K. Okay? So therefore, left hand side everything is known. For an ideal gas, U2 is CVT2, U1 is CVT1. Now here Mi is known, M2 minus M1, already we have found that, and Hi you substitute as CPTI, and the value of Cp for air is 1.004, you take this value kg K. So two unknown is there, Q and W. So to find out any one of them from this equation, you have to know other one from an independent equation. What is that? That is the work done. This work I have told the piston is moving slowly, that at all stages its mass is balanced by the pressure, and since its mass or weight is balanced by the pressure force or the pressure, means that the pressure remains constant at 300 kilopascal. So this does PdV work, and this PdV work at constant pressure amounts to be pressure P1, that is the constant, into V2 minus V1. Because PdV work, W is integral, this is PdV work, because the piston is moving very slowly and always there is a balance between piston weight and the pressure of the air. So if pressure is constant, it comes out P into V2 minus V1. We know V2, we know V1, we know P1. So therefore independently we can find the work done, that is the PdV work at constant pressure, so we can find out Q. And the value of work and Q comes out to be, I tell you, the value of work is 225 kilojoule, 225, this is positive, means this is done by the system, and Q comes out to be minus 819 kilojoule. This minus sign indicates that heat has come out of the system. That means heat finally is not going in, which we have taken and has written this equation, but finally it has come out. So this is the problem. Clear? Okay. So here we see the difference between the earlier problem is that there was a turbine work, instead that there is a piston expansion, that PdV work. Here more important concept through this problem is there, that even in an open system we have PdV work. That PdV work is not only for a closed system. This is an open system where there is a inflow, but this is an unsteady open system, there is no outflow, but this air pushes the piston to go up. So therefore we can have PdV work even in an open system, but this work requires a quasi-static process or a reversible process, which we will discuss afterward. Very slow process, that always there will be a thermodynamic equilibrium of the system. Okay, then this is the problem. Now we will discuss the second law of thermodynamics. The second law of thermodynamics is very conceptual regime, or rather we can tell is a very conceptual area. Now first law we have seen, it is the conservation of energy principle or law of conservation of energy. Second law, as I told earlier in the introductory class, is an independent law which puts a directional constraint on all natural processes, or a unidirectional characteristics of natural processes. It apparently means that all natural processes takes place in one direction, but it is not like that, it is not so. Rather we can understand it better in this way, that yes, there are natural processes which always takes place in one direction. For example, the fluid flows from high energy level to low energy level. The water runs downhill. There is a statement like that. That means if water is there at the top of the hill, it spontaneously comes down because the potential energy is high at the top and low at the bottom. Similarly, the heat is always transferred from high temperature to low temperature, not from low temperature to high temperature. Similarly, the electric current flows from high voltage to low voltage. the mass transfer of a species takes place from high concentration to low concentration. Okay, so these are the examples of natural processes which takes place spontaneously, occurs in one direction. There are another class of problems which are not spontaneous process, but which can be made by man. They also take place in one direction. What are those processes? Some example I am giving you. That consider a rotating wheel. Now we stop it by applying a brake. Then what happens is that mechanical brake, for example. Then what happens? The wheel comes to rest, and the brake shoe and the wheel gets heated. That means its temperature rises. And let us consider the entire system is insulated, no heat transfer with the surroundings. This process, from first law of thermodynamics we can tell that the kinetic energy is converted into intermolecular energy. So total energy within this system remains same, but the kinetic energy is transferred in the form of the energy is transferred from the form of kinetic energy to the intermolecular energy, for which this has become hot. That means the temperature has increased. But there is no way by decreasing the temperature of the wheel and the brake to set the wheel in motion. So this is a one directional process. Similar is the case if you take liquid in a container, and if you stir the liquid, then you will see the liquid temperature increases. And in that case also we tell that for stirring the liquid, some mechanical work is done on the system. If we consider liquid as a system, the mass of the liquid, the mechanical work which is transferred into this liquid has increased this intermolecular energy, for which there is an increase in temperature. But there is no process by which temperature is brought down and we get back the motion of the stirrer. This is not possible. These are known as adiabatic transformation of kinetic energy into intermolecular energy, or mechanical energy into intermolecular energy. Afterwards we will see these are known as dissipation of energy. And this type of processes are one directional or unidirectional. But there are number of processes which are not unidirectional. For example, you can heat a body from a lower temperature of T1 to a higher temperature of T2. But at the same time you can cool the body from this higher temperature T2 to the lower temperature T1. So in that case the process can be reversed. What is the directional constraint? For example, you can compress a gas from a lower pressure and temperature to a higher pressure and temperature in a piston cylinder arrangement. And you can expand the gas from the same higher pressure and temperature to the lower pressure and temperature. So the process can be reversed back. So many such processes in nature can be made to occur in both the directions. But these processes, when they occur in both the directions, they make some permanent changes in the surrounding, which I will come later on, and they have to follow a particular principle because of the change in the surrounding. So when they go in one direction and they come back in other direction, we make the process to occur in both directions. There is some permanent change in the surrounding for all natural processes, and that change in the surrounding is expressed in the form of some principle. Okay, and that principle has to be followed by any natural processes, and that principle or that law, that is basically the second law, is expressed in various forms. In various forms, people working in different area, they use, for example, people of material science, people in mechanical engineering, people in electrical engineering, people of physics. So people in chemical engineering working in different area, this directional constraint which is imposed because of the occurrence of the process in both the directions as a permanent change in the surrounding is expressed in different forms. But the genesis is same, that this imposes a directional constraint. Now this will be explained further afterwards, but now from the viewpoint of mechanical engineering, there are two classical statements for the second law of thermodynamics. One is Kelvin-Planck statement, another is known as Clausius statement. But before coming to this statement, I will tell you that certain definition. So definition of, first I will tell you the definitions of thermal reservoir. Thermal reservoir. thermal reservoir is considered to be a body with very high capacity, heat capacity, so that if it supplies heat or receives heat, supplies heat to somebody, some system, or receives heat from some system, its temperature does not change. Its thermal capacity is very high compared to this heat transfer. This is known as thermal reservoir. When it supplies heat, then it is known as source. The reservoir is known as source. When it receives heat, the reservoir is known as sink. So this is known as thermal reservoir. This is the concept of thermal reservoir. Now, with this concept, we now go to the concept of heat engine. Heat engine. What is a heat engine? Now, heat engine is defined like this. Basic definition of heat engine is like that. It is a device. Let us write this, heat engine. Afterwards, I will use HE only. Heat engine, where a working system operates on a thermodynamic cycle. You know what is a thermodynamic cycle? That means thermodynamic cycle consists of a number of processes executed by a system such that the system comes back to its initial state. After the last process, the final state and initial state become same. The final state is the initial state. It operates, heat engine, on a thermodynamic cycle. The working system operates in thermodynamic cycle, and it receives some heat. That means it has a heat input from a thermal reservoir. Let us consider a temperature T1, and it has an work output W. So this is the basic definition of heat engine, that which has an heat input Q1, and to have an heat input it has to have a thermal source T1, and from that it has a work output. That means it converts heat into work. Now in this respect, we have to know that for a continuous conversion of heat to work, the cyclic operation is required. A cyclic operation is required for continuous conversion of heat to work, and that is why the system has to operate on a thermodynamic cycle. So this is the basic definition of heat engine. Takes a heat input and delivers work. Now from thermodynamics first law, we can write that this work equals to Q1. So as far as the basic definitions of heat engine and first law of thermodynamics, the conservation of energy, I am right up to this point. But the second law, which is formulated again, I tell you, from the basic observations in nature, tells no, this is never possible. You can never convert the entire heat into work continuously in a cyclic process. So what then you can do? Thermodynamics second law tells first, no, this you cannot do. So what you have to do, if you want to convert work from heat Q1, then you have to reject some amount of heat for which you require another thermal reservoir, that is sink. This is source T2, which is less than T1. And in that case, W will be Q1 minus Q2. So which means W is always less than Q1. So the entire Q heat which you receive from the source cannot be converted into work continuously in a cyclic operation by a heat engine. So this is the concept. Now in this context, we define thermal efficiency of a heat engine as the desired output W divided by heat input Q1. This is given by eta. So therefore eta is W by Q1, or one can write Q1 minus Q2 by Q1, that is equal to 1 minus Q2. By second law, W is always less than Q1. That means Q2 can never become 0. Q2 has to be greater than 0 and W has to be less than Q1, which means eta always less than 100%. That means a heat engine can never reach 100% efficiency. But here one very important point is there, that this heat engine can never reach 100% efficiency. That is, even the heat engine is an ideal one and it consists of all ideal processes. That means reversible processes which I will come afterwards, even in the most ideal case that in absence of all dissipative effects and everything, then also this cannot achieve 100% efficiency. Here is a very strong concept that sometimes we tell a generator cannot attain 100% efficiency, electrical motor cannot attain 100% efficiency, and a mechanical transmission system cannot attain 100% efficiency. This is because of practical things, dissipative effects, friction, hysteresis, all these things come into picture, electrical hysteresis, magnetic hysteresis. But in an ideal case, we can conceive of such systems with 100% efficiency. But here, we cannot conceive of an ideal heat engine in absence of all frictional and all dissipative effects to attain the 100% efficiency. Then this imposition by the second law is imposition even on the ideal system. So this is the heat engine definition. Okay. Now, I will tell you the Kelvin-Planck statement and this is the Kelvin-Planck statement which tells it is impossible for any device that operates on a cycle to exchange heat with single reservoir and produce a net amount of work that I have described. And Clausius statement tells it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. That spontaneously heat cannot be transferred from lower temperature body to higher temperature body. These are two statements. So now these two statements are equivalent. That means if Clausius statement is invalid, then Kelvin statement is invalid. If Kelvin statement is invalid, Clausius statement is invalid. How? Let me prove that. Let us consider the Kelvin-Planck statement is invalid. That means there is a temperature T1 and let us consider a heat engine operating, violating the Kelvin-Planck statement by exchanging heat. Let this is Q1 with this T1 temperature and develop work. And let us consider that a system that takes so this is the Kelvin that is the violation of Kelvin-Planck statement T1, and we consider that this there is a heat pump. Of course, we have to tell the heat pump, before that you have to know the heat pump, otherwise it will be difficult for you to know. Let us see that we go back to the definition of heat pump, then we will put this, sorry, otherwise it is very difficult to understand the equality of the two. A heat pump or a refrigerator, heat pump or a refrigerator, just the reverse of the heat engine. That means what it does, it takes heat from a low temperature body and pumps heat to a high temperature body, but it is not possible according to Clausius statement, but it takes work from outside. So giving work from outside, one can take heat from a low temperature, T2 is less than T1 or T1 is greater than T2 to a high temperature body. In this case it is possible, it takes work, not spontaneously without any effect in the surrounding. In this respect, if you write the conservation of energy, Q1 becomes is equal to Q2 plus W. So Q1 is equal to this Q1 given equals to Q2 plus W. So this W taken, this is just the reverse of heat engine. In this context, two things are defined: coefficient of performance. Just like thermal efficiency of a heat engine, we define coefficient of performance, COP, simply. Now, when our desired objective is to pump heat to higher temperature, then we call it as a heat pump. When our desired objective is to take heat from a lower temperature, we call it as a refrigerator. A refrigerator and heat pump is the same device. You will see in your house that if you stand the side of the refrigerator, it will be hot. It is exchanging heat to the surrounding. So if you think in that terms, I get heat from the refrigerator outside, that it is a heat pump, and if the inside of the refrigerator, what is the evaporator box, that is the deep fridge, so there the cold press is there where the heat is being taken. So if the desired objective is Q2, the taken heat from the low temperature is refrigerator, and the desired objective is Q1, then it is heat pump. So therefore, COP of a heat pump is given by the desired objective Q1 by W, and COP of a refrigerator is Q2 by W. And from the first law, we can write that W is nothing but Q1 minus Q2. So therefore, Q2 by Q1 minus. So with this definition of heat pump or refrigerator, now we can prove the equivalence of Clausius statement and the Kelvin-Planck statement. Okay? Kelvin-Planck statement and Clausius statement. Kelvin-Planck statement and Clausius statement and Clausius statement. Now you see the equivalence of Kelvin-Planck, and let us consider, that means equivalence means if Kelvin-Planck statement is not valid, then Clausius statement will also not be valid. Similarly, if the Clausius statement is not valid, Kelvin-Planck statement will not be valid. Let us consider the Kelvin-Planck statement is invalid. That means there is a heat engine which takes heat Q1 from a source T1 and develops work W. And develops work W, here I write. There is no other reservoir. That means the entire Q1 is converted to W, violating the Kelvin-Planck statement. It operates with single fixed reservoir. Now we consider a heat pump or a refrigerator, a heat pump or a refrigerator which takes heat from a low temperature body T2, which is lower than T1 here. In this case, lower than T1, takes some heat QL. And this heat pump is run by this heat engine. That means the work developed by the heat engine is given to this heat pump to run. Okay? This is the heat engine and this is the heat pump in the opposite direction, cycle. And then this rejects heat QH. Now this QH is what? QH is QL plus W, and W is what? W equals to Q, QH plus W. Again from the heat engine conservation of energy, W is Q1. So okay, W is Q1. So QH is QL plus Q1. So QH is QL plus Q1. Okay. Now therefore you see that the combined system as a whole does what? This takes heat QL from the low temperature to the high temperature, because the high temperature source receives the heat, it gives Q1 and takes QH. It receives a heat, QH minus Q1 is QL. That means if you see the reservoir source, this high temperature reservoir, it gives it Q1, receives it QH. So it receives the net heat QH minus Q1 is QL. That is what is being taken from the low temperature T2. So therefore the combined system spontaneously takes heat from T2 and pumps it at T1 higher temperature without any other effect in the surrounding, because this work is internal. That means this heat engine work is driving the heat pump. So combined system does not make any change in the surrounding, without making any change in the surrounding, lifts heat from low temperature to high temperature. That means if the Kelvin-Planck statement is not valid, Clausius statement is also not valid. Similarly, we can show that if the Clausius statement is not valid, that means spontaneously heat can flow from low temperature to high temperature without any other effect in the surrounding, then Clausius statement will not be valid. So this is left as an exercise to you, and you can see in any thermodynamics book for this. Time is short, so I am not doing that. So only one I have proved that if Kelvin-Planck statement is invalid, Clausius statement is invalid. So it violates the Clausius statement. Similarly, if Clausius statement is violated, Kelvin-Planck statement is also violated. So after this, I will show you a practical figure that this is of a typical steam power plant. You know the steam power plant from which we get electrical energy, but the steam power plant layout is like that. From your popular knowledge you know, but I am not going into any details of that. There is a boiler where the combustion takes place of a fuel, usually coal, and the high temperature gas of that after the combustion hits the water in the boiler. Water is the working substance. This is converted into steam, and then this expands into turbine to give work. Then after expansion, the low temperature and low pressure steam is passed through a condenser where it rejects heat to the atmosphere. Usually the atmospheric water is a water from the atmosphere is taken as the cooling water, which takes the heat from the steam to condense. Then it is given to the pump where it takes work and pressure is boosted to that of the boiler pressure. So this is a thermodynamic cycle, and here you see that energy source, that is the furnace where the combustion takes place and hot gas gives the heat. That means here the working system water takes heat. So this is one reservoir, and in the condenser where the steam after expansion is condensed is the sink, the low temperature reservoir, that is cooling water from the atmosphere. So you see that this is a heat engine where we have two reservoirs, that furnace of the boiler and the cooling water from the ambient or atmosphere at the condenser. And as a result we get a net work output, which is the work output from the turbine minus the work input to the pump, which is much less compared to the turbine work. So this is one good example of a heat engine, which is a typical steam power plant in practice. Okay. Now we close this module here. Next we will start the other things. Thank you.